tasks. So I would assume that you have a basic idea of artificial neural network, ANN, ANN, and forward pass and the back propagation. If you uh, know about forward pass and back propagation, then it would be easier to understand some of the architectures that are specifically for natural language processing and the sequence modeling basically. So I just want to ask is how many of you are comfortable with NN and NN uh, forward pass back propagation, the basic idea about artificial neural network. So I hope you have that idea. Yes or no? I got some replies that yes. What about others? Okay. So all of you must have our at least basic understanding of NN, where you have a dense neural network. For example, let's say if you have only one input layer, hidden layer, and an output layer, then uh, in dense neural network, at each node, so input layer where you give the inputs. So this is two input NN, and at each node or perceptron, you would say, or neuron, there is a basic operation called weighted sum. So for example, if x1 and x2 and corresponding weights w1 and w2, then it is w1 x1 plus w2 x2, and adding bias, and you pass it to some activation function that gives you the output of that neuron, right? So at each node you have uh, weighted sum and adding bias, passing to an activation function for nonlinearity, and you get the output. And then further in other layers, that output becomes the input. So during the forward pass, input is processed, and towards the end, uh, for example, let's say this is in last node, you get the output. So this is the forward pass, and those weights are updated during the back propagation. So you might have some output, uh, predicted output, which and since you are training on particular data, you might have some ground truth. So depending on the actual output and the predicted output, you define a loss function, and you train the model by minimizing the loss. And usually we use gradient descent or their variants to update the weights. So usually new weights is nothing but old weight minus alpha into gradient with respect to old weight, and that alpha is called learning rate, and this is called the gradient. It is just partial derivative of that loss function with respect to the w old, and you update all the weights. So w new could be w1, w2, w3, w5, w6, and so on. So you update all the weights, and in the next iteration again you give the input and check what is the output and what is the difference between the predicted output and actual output. So a classical neural network, uh, it was proved that can solve with even a single hidden layer can solve any type of problem. However, they are not suitable for sequence modeling task. So in sequence modeling task, for example, let's say if you talk about text, uh, I like this, and then you want to predict the next word, what could be the next word. So that depending on the previous tokens, previous inputs, and those tokens can be represented by a number. So you might have studied somewhere in the previous sessions that these words are represented by a numerical representation, usually popularly known as a word embedding. So in basic neural network, for example, let's say this each word embedding has size of 10. So these word vectors are size of 10. So let's say if you have three vectors, and so each time you so for predicting this, let's say you give all those 30 values as an input to a network. So there are various problems with this approach. One is the basic RNN, basic ANN network uh, does not have a notion of ordering. So, for example, here in this sentence, like is coming after the I, and this is coming after the like and I. In artificial neural network, there is no notion of ordering there. So everything you give the input as once. Even in case of, let's say, in an image also, let's say if you have a 2 cross 2 image, so there are four values of pixels are there, and if you give it to the input to the neural network, the structure of that image is does not matter in case of neural basic neural network. So there is no inherent or implicit idea of ordering. So there are some problems with the neural network architecture. So one is the ordering. So there is no notion of ordering, and you have fixed size input only. Whereas in sequence modeling, especially in case of text, for example, let's say uh, the same example, uh, I like this uh, NLP course, and I'm creating a language model that predicts next word based on the previous words. So, for example, let's say I want to predict like. So the previous word is I. So I is an input, uh, works as an input. So initially, let's say the word embedding size is 10. So you have 10 input to a neural network. However, in case of, let's say, this, it could be 20. So however, in artificial neural network, you define fixed input that will further goes to the hidden layers and so on. So there is no fixed. They work only with a fixed input size. Whereas in case of NLP related task, where you or the sequence related task, in the sequence modeling, you might have input of varying size, right? And there is more common problem with, not only with for the sequence modeling, even for the image related task, no parameter sharing. So there is no notion of parameter sharing concept here in NN. So these are the problem with artificial neural network. Don't worry, I'll go to the slides. uh, However, just giving a background of it from where we are going to start with, right? So don't worry, you'll just have to bear with me with this, uh, I mean, bad handwriting for some few minutes. So problem with these are the problem with NN. There is no notion of ordering. It only works with a fixed input size, and there is no parameter sharing. So, for example, let's say if you have an this neural network, uh, where this is your input, this is your hidden layer, and this is your output. Uh, let's say x1 and x2 are the input, and output is O. So this particular node, input one node, connected to hidden one node. So if you see here, there is a unique weight between each uh, pair of input, and so in each pair of two nodes, for example, I1 H1 you have W1, I1 S2 you have W2, I1 S3 you have W3. So these weights are unique with respect to each pair of nodes, and there is no parameter sharing, and it becomes a real cumbersome to train a model on a data where data is high dimensional. For example, let's say if you have even if you have, let's say, uh, 64 cross 64 image. So you can see here, if you want to give it as an input to a basic neural network, you will have a input size 1 into 64 square. So these many nodes needed for the input. So, and nowadays even a single image in your mobile have size 1024 into 1024, though it is nowadays it is quite small. So basic NN you cannot use for uh, image related task or the sequence related task. And sequence related task again, in sequence to sequence modeling, they further complicate the things due to the varying input size and the no notion and the notion of ordering. So what are those tasks basically when we say sequence modeling or sequence related task? So let me share the presentation with you. It's okay. So from implementation point of view, that it's fine. That uh, just I just want to know whether you know the theoretical concept of NN or not. Okay. So regarding this session, you have two parts. First, we'll talk about theory of specific neural networks architecture called recurrent neural network and its variants like LSTM, GRU, and further BiLSTM and bidirectional GRU. We'll understand how they work and what is the foundation behind it. And assuming you all know basic ANN feed forward and back propagation, and we just got motivated by the fact that ANN is not good for sequence modeling task. And in the second part, so this will be the session one for today. And in the session two, uh, you'll get a demonstration or hands-on on text processing uh, and so text classification in PyTorch. So you will see that hands-on in the session 2, which will start around 4 p.m. So in theory task, we'll talk about RNN and its variants. So let me share the slides. Okay, so one second, I'll take a minute, just a second. Let me. All right. So, well, I hope my screen is visible to you. Okay. So, some of this slight credit goes to some of image that I have used uh, are available on this block as well. Some of the notions and the notations that I have used, you will find out in the NG course as well. And this is the main backbone of transfer related architecture that we are maybe in the next session we are going to discuss about it. So you till now you have studied about natural language processing where uh, you instead of you learning the computer language, NLP is the just opposite that you teach computers to speak our language. And there are mainly two key areas: natural language understanding and natural language generation, that you have already covered in the previous session. And there are lots of uh, examples are there, applications are there, voice assistant, spam filters, machine translation task, where you were given in a one language, it converts into another language, and sentiment analysis and predictive text and autocorrect. Even nowadays, you see when you write email on Gmail account, Google automatically predict the words or the sentence that you want to write. So in language modeling, there are three primarily types of language models are there. Statistical language models, where you use n-gram based approaches to understand and or to create the language models. Later on, researchers have proposed neural language models, where you use variants of neural networks like RNN and their variants like LSTM GRU. And later on, language models have been has have been come up with a recent advancement in terms of transformer based models, and all those GPTs and those LLMs that you see and you use nowadays are based on the transformer based model. And all those models basically built on three mathematical model: so next word prediction, mask word prediction, and the replace word detection. So how they are trained? So given the corpus, then those neural network, those models are trained to predict the next words given the previous words. So n-gram based models have been use probability based concept of conditional probability, where given the previous words and it you calculate the probability of the next words. And in the mass words prediction, randomly some words in the sentence are masked, and given the context and given the other words as a context, model tries to predict the mass word. And that another variant of it is replace word, where random words are replaced with other words, and model uh, try to predict that word. And due to with the help of training, the model is trained, and towards the end, when model is converged, that is basically trained, and then it is able to identify the replace word. So how you define mathematical model of natural language? How you define the sentence probability? Unlike simple points or data, where you can just simply define the probability of that points or vector, here a sentence probability is defined by the product of the probabilities of the tokens given the previous tokens. So, for example, let's say probability of I saw a cat on, and you want to predict something next word. It is defined by probability of I multiply with the probability of next word given the previous word. multiply with the probability of A given the previous probability of I saw. Uh, then probability of cat given the previous I saw a. So formally it can define a whole sentence probability is defined as a product of the probabilities of its tokens given the previous tokens. Now, how you compute that probability of particular token given the previous tokens? So statistically, there are n-gram based models, and in deep learning, there are neural network based architectures to compute this. And how the generation happens? So, given a word I, and you want how it predicts the next words. So from all the corpus of data, for example, you have training data and that have let's say 10,000 tokens are there, right? So for all the 10,000 tokens of the words, it calculates the probability given the word I, simply conditional probability, and the word which have the highest probability is selected as the next word. uh, and then next time, given those two words as a previous context, uh, the probability of other tokens has been calculated, and so on. So each time, uh, every time it generates probability of the next word given the previous word. So this is how generation happens using a language model. Still, we have not started how to do it, how it is done using uh, natural language tasks. If we have if we see a high level pipeline of any neural network model, the neural language models basically, uh, because we are sticking towards the language tasks. So if you see here, uh, neural network takes the context word, the previous words, and those words are not directly given. Obviously, the numerical representation of those words, basically word vectors or word embeddings, are given to the neural network. Neural network towards the end of the output generates a vector which hypothetically represent the context of that those inputs, right? And that context is given to the linear layer. Linear layer is simply, it could be simply a dense layer having the output nodes equal to the number of tokens that you have in your corpus. And that linear layer towards the end using softmax generates the probability of corresponding to all the tokens, and which have the highest probability, the model picks that the next word. So I saw a cat on a taking as an input, it generates the output based on which have the highest probability. So words are always represented by embeddings, right? You might have understood this that's in the previous session. And once you get the output, obviously there might be chance that your model is giving output something else, and the actual word in the sentence was something else. So then you take the then you define the loss uh, where predicted word was something else, and the so difference between predicted words and the actual words defined as a loss. And for example, model predicted word cat, model predicted was this with the highest probability. However, the actual target was cat. I saw a cat, which the model giving the low probability. Then you define the loss, which is the log loss with respect to the cat, and it decrease other probability, and model tries to increase the probability of that particular word. So that model is trained and minimize the loss. So usually a log loss, categorical loss you use for the loss function. Uh, coming Before coming to that, let's uh, so what are those neural network based architectures? So there is a specific type of architecture called recurrent neural network. for sequence to sequence modeling task. So when we say sequence models, so what type of sequence data is there? So there are various examples, like for example, speech recognition, where you have a audio wave as an input, and you the output is the text sequence, right? So speech recognition, which is a sequence to sequence application or problem. In case of music generation, another example of sequence modeling, where input could be nothing, or it could be a single integer that might represent a genre, or the type of song you want to generate. And based on that single input, output is a wave sequence. So that an example of sequence modeling, where input is one and the output is a sequence. There is another sequence modeling concept called sequence task is sentiment classification, where your input is sequence and your output is one. So given a text sequence, the output represent whether it could be 1 to 5 rating, or it could be simply positive or negative, 0 or 1. DNS sequence analysis is again an example of sequence to sequence, where X is your DNS sequence and Y is your DNA labels. This is popular problem called machine translation, where your input is in one language and your output is in another language. There is another called video activity recognition, named entity recognition. In all those cases, there are varying type of uh, problems are there. So for example, let's say named entity recognition. Uh, given a sentence, you want to find out particular word is an entity or not. So you might have, let's say, W1, W2, W3, and W up to WN words are there in the sentence, and you want to predict whether this word is an entity or not. So the output could be simply one or zero, zero or one, where one represents it is an entity and zero represents it is not. So based on that, you have different architectures are there, and RNN called one to many, where your input is one and output is many, and many to one, and many to many. In case of many to many, this example of named entity recognition is you can see it is a many to many. Similarly, in machine translation task, where you give input in one language, it generates output in another language, L2. This is also an example of many to many, but there is a difference between these two tasks. If you see in many to many, in case of named entity recognition, the output length and input length are same. However, in case of machine translation task, a sentence written in one language might have a different length with the output language. So, to understand in detail, let's take one example of many to many. For example, let's say there is a word level. Let's say we want to have a word level sentiment labeling task, and that also a many to many with both size are same. So, whereas given X, this movie was absolutely amazing and very emotional. We want to find out so word level sentiment labeling. So whether that word represent a sentiment or not. So if you see here, corresponding to this, you have zero. Corresponding to movie, you have zero. Corresponding to was, you have zero. Where for corresponding absolutely and amazing, you have one, and then for and zero, and for very and emotionally, you have one. So both element input and output has shape of 8. So there are 8 inputs, 8 outputs, where one indicates the positive sentiment words, while zero indicate the neutral or non-sentiment words. To understand this in detail, uh, let's have some notations. Let's see some notations. So we'll in index every element in the input as a superscript by the number. For example, this particular first input, this will write it x1 and then movie x2 and so on. So x1 will be this, x2 will be movie. Similarly, for the output, we'll have y1, y2 and so on. Whereas the last is basically yt. So this is your xt and this is your yt. And let's say you have t tokens in it. So this particular problem, word level sentence labeling, if you see here, the size of t input and size of output both are same. And in other cases, in other problems, they might be have a different in other problem. For example, uh, in music generation, you might have only one input, so tx is one, and whereas ty could be n. However, this where your tx and ty's are same, it is easy to understand the concept of recurrent neural network. So we'll take this as an example. And obviously, in data set, you given data set, you might have uh, various input text one, two, three, and corresponding the output uh, might be there. So in your data set, iterating through all those input text, you have I as an iterator, and T superscript is for the teeth token in that. So how RNN network works, and that we had already discussed why you should not use standard neural network for sequence task, and there are various problems with it, that, and we have already discussed it. So to capture the notion of ordering, uh, okay, let me have a so given an input, for example, let's say x x1 so according to notation we are writing x1, x2, uh, x3, x4 and so on. In recurrent neural network, instead of giving all the input at once to the network takes one input at a time, and one input goes to an RNN unit, usually popularly represented by these dots and this block, which says this is input, and this is simply a RNN unit. Could be simply a basic neural network having an input layer and the hidden layer and the output layer. Right? So simple neural network unit is there, and we are giving only one input this, and this RNN unit uh, takes the input and process it, and it generates the output. Let's say we call it y1. However, unlike basic neural network, it generates we take before output, we take the representation of that x1 as a context vector, so that in representation a1 is nothing but a vector which gives you the state or the context of the word x1. So you can think of this as a vector which takes the context from here, and we pass this to the second RNN unit, which takes the x2 and context from the previous word, and it generates the output y2. In turn, it also gives you the context vector that goes to uh, third RNN unit, which generates the output y3. Now, if you see here, Uh, Y3. So unlike other neural network, Y3 here not only dependent on the current input, which is X3, it is also having the contextual information from the previous words, which is A2, which uh, takes the context of both X1 and X2. So Y3 is not only dependent on X3, it is also dependent on these two. And one by one, sequence to sequence, uh, the input is processed and the output is generated. And you pass the context from one RNA to another RNA. And towards the end, where you have XT, which takes context vector AT that generates the output YT. If you see here in the first RNA unit, since there is no previous word or previous context, you pass random vector. So this randomly initialized vector as a context. It could be randomly initialized or simply a zero vector for initial RNA. So vector of zeros is given as a context, and each RNA unit generates an output and give the context to the other unit. However, it is this particular RNA architecture is for the type of task where your Tx is equal to Ty. So you have X in Tx input and correspondingly you have Ty output. I hope you are getting my point. So if you have any question in between, you can just write it on the chat. Uh, Randomly, I'll check the chat and see if there is any questions or not. All right. Uh, a compact representation of that architecture is also represented something like this, where you have this loop sign, which uh, represent a recurrent notion of the inputs, and this uh, yes, the loops key. Okay, so in the next uh, layer, the previous layer in context is given. So this is you can see a rolled version, or and this is the unrolled version. So if you expand this basically this is represented by this. And since it is a neural network, so neural network, when you give the input, let's say xt, let's say this is a vector of size 1 2 3 4 5, 1 to 5. So 5 inputs are there and some hidden nodes are there as an hidden layer. So you there are obviously weights are involved. So weight in algebraic notation can be represented in terms of matrix. So there are three weights are in matrices involved. WAX, which is in between input to hidden, so number of hidden neurons into and NX is the size of the WAX. So WAX is involved in between input and hidden, and there is uh, hidden to output. There is one WYA is involved, which is the size of it is number of nodes in the output to the number of hidden neuron, and there is WA involved in between when you calculate the hidden context vector from the RNA unit. So these three weight matrices are involved, and obviously these the weight matrices are learned during the training time. So this weight matrix is basically the WA is the memory the RNA is trying to maintain from the previous layer. It is harder to interpret this one, so it is easier to um, have a drawing of this to the unrolled version where you have input uh, given to RNN unit, you get the output, and it also takes the context from the previous sequence, previous words. So, given those weight matrices, how you formally define the output? So for example, let's say if we talk about A1, so A1 is nothing but uh, weight matrix which is involved is WA multiply with the previous context vector or state plus weight matrix between the input and the hidden WAX multiply with the x1. So it is nothing but simply a weighted sum plus bias. Extra what we are doing, we are having context from the previous word, which also multiply with the weight matrix, corresponding weight matrix. And once we have the weighted sum, we pass it to activation function. Let's say we're calling it G1. We get the contextual representation that we pass to the next RNA. And using this contextual representation, you also calculate the output, which is nothing but weighted sum that involves uh, weight matrix in algebraic representation represent have WYA into A1 plus bias passing to activation function gives you the output. This is for A1. If you write for AT, that basically represent AT minus 1 and this XT. And similarly, this is AT. Usually, this activation function G1 and G2, since A1 is basically in internal representation is there in involved internal layer, usually you use ReLU or 10H. And for the output, it depends on the type of task you are doing. So if output is only 2, then you use sigmoid, or if your output is a multi-class output, then you use softmax. So basically you have uh, two equations, AT and YT. And this even this complex equation can be further simplified, where you uh, come up with a weight matrix WA, which is nothing but take those two matrices WA and WX and horizontally concatenate it. So horizontally put together, then you can think of this as a WA. And that AT minus 1 and XT, if you put it together, vertically stacking you do, then the weight matrix that you get, so sorry, this another matrix that you get is basically your AT minus 1 comma XT. And when you multiply this matrix to WA, it works similarly that this, and you add bias, pass to activation function, you get AT. And your y T is also WY into AT plus BY. This. And so WA is nothing but WAX and WAA stacked horizontally, where this is nothing but these two are stacked vertically. Right. So this is the most simplified version, and this is basically the idea of RNN. So this each time you calculate the context and get the output, and you pass to the another layer, which another RNN unit, which not only take the current input but also the context from the previous layer. So any question in this point? You can write it on the chat. Is there any questions, or should I go ahead? Or you want, if you have any confusion or if you did not understand any part of it, just let me know. I will revisit that part. Okay, taking it as yes, let's continue. So just focus on these two equations: the context representation or context vector, that how we calculate the context vector, and the how we get the out. Using that context vector, you just uh, multiply with weight matrix involved in the output layer and header layer, and then add the bias and pass to activation function, you get the out. So second, let me. So each time, each RNN unit gives you some output: y1, y2, y3, and this context vectors are given. And the output that you have here, you might have if it specifically talking about the supervised learning where you have y and x both, you might have y means y1, y2, y3, and so on, yt. You might have the target output. However, in this the output that you are getting is a predicted output. So loss here also, it is defined simply the difference between predicted output, let's say calling cap, and actual output yt. However, unlike basic neural network where we define loss simply predicted output and the actual output, here there are multiple RNN units are there. So you take the summation of the all the RNN unit loss or differences between predicted and actual for all the RNN units. So the whole loss is calculated as a summation of the losses at each RNN unit, and you take the sum. And to train the network, which involve basically the updating on those weights that are there in the RNA unit, backpropagation is done. And since you have a different RNA unit, consider this can be as a time stamped concept where each, so this is let's say T1, T2, T3, and TT. Backpropagation is done, and uh, specifically for RNA, it is known as a backpropagation through time. Through time is nothing but it start with updating the weights of the last RNA unit, and it updates all the weights in the previous layer. And the updation of weight takes place similarly that we had seen that you might have studied for neural network, where you use gradient descent or its variants. So it could be stochastic gradient descent, or it could be a mini Bayes gradient descent, or it could be gradient descent with momentum, or ADA grade or ADA delta, or you might have used ADAM optimizer for it. So specifically in RNN, this backpropagation is known as a backpropagation through time, where you update weights of each uh, node in the RNN unit. So you define the loss function, and this loss functions is usually it is cross entropy loss, uh, which is y log y predicted minus 1 minus y into 1 log of 1 minus y, and total loss is nothing but the summation over all the losses that you have in the sequence. So in the forward propagation, you calculate the output and you calculate the loss value, and towards the end you calculate the total loss, and uh, we update the weight from last layer to the first layer in a sequence. Similarly, how you update the weights in the basic neural network from last layer to the first layer, going through all the hidden layers. Since right now the example that we have seen uh, of only one RNA architecture where your Tx is equal to Ty, you have input and the output having the same length. However, in some other cases, they may not be equal. So you might need a different architecture for it. And this idea was inspired by Andres graphic blog. Mainly there, this image is all the type. So one to one. So one to one, basically, it's not a RNN, but uh, if you're talking about one to one RNN, it is nothing but simple neural network. There is one to many where you have only one input and multiple outputs. Specifically in this case, particular problem that you can think of one to many is, let's say music generation is there. You have a single input and you want to generate a sequence, right? In that case, how the architecture will look like? So in one to many, in the first RNN unit, you give the input X, which takes the initial zero vector and generates one output. However, for the further subsequent RNA unit, you take the output of first RNA unit as an input to the other RNA unit, and so on. So Y2 is given to the as an X3 to the next RNA unit, and so on. So that Y2 is not only dependent on the first input, however, it also depends on the previous output as well, because output is the sequence. So the ordering of Y2, so Y2 not only depends on the input but the previous output as well. Similarly, in case of many to one, for example, sentiment classification task or fake reviews identification, fake news identification, where given a text of news article, you want to predict whether this is fake or real. So the output is only one. Then what you do, you take the inputs and you pass it to the RNN unit. You don't collect the output at intermediate layers. You intermediate RNN unit. You take the output only at the last RNN unit. So you learn the context from whole sequence, and towards the end of the sequence, you get the output. So that why predicted is not only dependent on the last token, but the context from all the previous tokens. This was the example that we have seen in the previous slides called many to many, where Tx is equal to Ty. Whereas in many to many architecture, where you don't have same length of input and output, you have a special type of architecture called encoder and decoder, where encoder encodes the input. It takes the input and pass the internal representation, also known as a hidden state, to other RNA unit, and towards the end it gives you single hidden representation, or basically the context vector that captures the information from the previous sequence, which goes to the decoder unit, and decoder unit generates one output at a time. So in decoder there is no input. However, it generates the output from the context. Obviously, decoder generates one by one. So here for other RNA unit, this becomes the next input, and so on. So for many to many with having different TX and TY, what do you think? What are the tasks or examples that you can think of? Write it on the chat. Some of the uh, example of many to many sequence modeling where input and output are different. Can you think of some problems linked in this? So one question was regarding the quiz. So there will be two quizzes. Yes, Google Translation is Google Translate is one example of many to many. Any other? So machine translation, apart from machine translation task, can you come up with any other example? Okay, so this is for you. Find out and explore what could be the other uh, problems for it. Now, in sequence to sequence modeling, you though RNN are solve our two problems. One is it has inherent notion of ordering in the sequence, and it can capture the ordering by processing one token at a time and passing the context to the other layers. However, there are some issues with it. One of the popularly known issue is the vanishing gradient problem. So what happens? So you might have heard about this vanishing gradient problem with neural networks as well, where in a deep neural network where you have multiple hidden layers, when you perform the back propagation and you calculate the gradient means derivative with respect to the loss function. Those derivatives, uh, when you want to update for, let's say, initial layers, so to calculate del L by del W, let's say here you have W1, uh, it involves the calculation of gradients from initial last layer to this layer, and the multiplication of those derivatives actually in turn calculate the derivative for this. So problem, what happens when you have this derivative chain multiplication, and when you multiply those numbers, eventually those gradients might be near to zero. And if you have those gradients near to zero, the problem is when you update weight using this equation, W new is equal to old minus learning rate and derivative with respect to W old. So if this value is near to zero, that this value becomes near to zero, and your new weights is almost similar to the old weights. So the problem is your weights are not updating, and if your weights are not updating, eventually in turn your model is not trained, or it is not uh, converging, or it is not training. So when there is no training happens, your model is not learning it. And if you see here, in RNN, this problem becomes naturally evident because you have a deep RNN uh, architecture. If you have, let's say, many RNN units, when you calculate uh, weight respect to the previous recurrent unit, derivative of weights with respect so previous RN unit, due to those derivative multiplications, the weights of the earlier layers eventually not updated, and if those weights are not updated, eventually there is no training happens because weights are not changing. So your some of your weights might not be updated properly because, for example, for computing the word was, we need to compute the gradient for everything behind, right? And multiplying fractions, when you multiply two fractions, it tends to vanish the gradient, means the resultant value goes near to zero because and and if those multiplication, and there is another counter problem called exploding gradient, where those gradients are having large values, so when you multiply it, it becomes a bigger and bigger. So though for exploding gradient, there are some solutions. So exploding gradient means your gradient value is quite large. Uh, so what the various approach that you can use truncated back propagation. So instead of updating all the weights in the way, do not update all the weights, update only some weights, though it is not optimal. There is a gradient clipping as well. So you can define a threshold. If the value of the gradient is goes beyond the threshold, then it is set to that threshold value. So you clip the gradient value. For vanishing gradient, when gradients goes near to zero and there is no training happens, uh, you apply different weight initialization approach, or another solution is you use LSTM or GRU networks. And these networks we are going to discuss in the next uh, just now. So in summary, what happens if you have a long sequence where you have many RNN unit, eventually gradient does not flow to all the RNN units. So your ordering or dependency or sequence cannot be captured. So uh, YT, which was expected to have the output based on the current input and the all previous inputs, eventually the information is lost. So RNN, though, are good at capturing the uh, ordering of the sequence and the dependency, however, they do not work well with the long range dependency. For example, YT is might be dependent on X1, which is quite far in the range. It might not be able to sustain that information. Any questions? Let me check the chat if you have any questions. Yes, I'm coming to GRU and LSTM. This was we had discussed just about the uh, RNN and its problem, and now we'll discuss about uh, GRU. Taking a small break of 2 minutes, then we'll continue with STM, GRU and LSTM. All right. Okay. So let's continue. So the story so far we have studied about RNN and how it captures the ordering due to its inherent architecture of RNN units, where it capture the context vector from the previous RNN units to calculate the output of the current RNN unit. And however, that architectures suffer from vanishing gradient problem because uh, that vanishing gradient problems also indirectly comes from the context vector as well. So if you see here, let me screen blank. Then so what happened when let's say this is your RN units and you have uh, last RN unit which okay. So if you see here, last RN unit, the context vector or the state representation 80 minus 1 have this information from all the previous RN units. So indirectly, it is capturing the information from x1 to xt minus 1. And think about it. This at minus 1 is a vector, and vector is nothing but some locations or memories. And think about this screen that you are seeing, white screen, as an at, where memory is there. And if I write uh, on this screen, think about this is an information which giving you the context. For example, here I'm explaining this RNN is basically the context that you are receiving. However, if I fill this with lot of information and that might be overlap, and I fill the whole board, whole screen there, you eventually at one point of time you could not understand anything. And once you could not understand anything, you tends to lose the context. Same thing happened when you have a large sequence where this size of this vector becomes the bottleneck, because in limited size or fixed size it is trying to capture the information from all the RNN units, and eventually this values become so overlapped, and so that information might be lost. That also leads to the vanishing gradient problem, or non-convergence problem in RNN. So RNN tends to lose the information due to this context vector bottleneck. So this is one reason. So this context vector bottleneck happens because every time an RNN unit generates a context vector, it captures the information from all the previous RNN unit. So what can be done here? So why not? So calculating the output yt, it takes the context from all the previous inputs. So it takes context from all the inputs. Why not find out which information is relevant? It might be there that yt do not depends on all the words, basically the context from all the words. It might be relevant to only particular word in the sequence. For example, this x3 and not x4 and x5. So why not this at minus 1 should contain all the information of xt? Why it is having the information from all the previous uh, inputs? That becomes the motivation for other architectures And researchers have come up with different architectures. So one line of researchers have uh, introduced the concept of gates. So gate, you can think of a gate which passes the information or not. So that if the gate is closed, then the information is not passed, and if gate is open, then information is passed. Something like this. So uh, that's what first. So some researcher have come up with a gated recurrent unit called GRU. So each RNA unit have the notion of gates. So before coming to that, this is another representation of the a single RNA unit. So in single RNA unit, where I was representing something like this, where A0 is given X1, it is calculating Y1, and it is also generating context vector A1. Right. So in general, this is AT, and this is AT minus 1, or this is XT, and this is YT. So this AT, the equation was this we have seen here, where G could be 10H or ReLU, and YT is nothing but WY into AT plus bias passing to activation function G2, which could be sigmoid or 10H. So this can be represented or visualized using another alternative diagram shown here, where AT minus 1 and XT together uh, pass to an activation function gives you AT, and if you just pass it to this AT with the another activation function, obviously weight matrix are involved, not shown in the figure. Softmax goes to the YT. So this is another example, and this notion will give you good understanding of other recurrent unit architectures. So instead of taking all the context, why not find out the relevant information, and that start the notion of the GRU. So in GRU, where it is also a recurrent neural network, where each RNN recurrent neural network unit, known as a gated recurrent neural unit, which instead of passing context, new context which consists of context from all the previous units, why not make it a gate where which either gives the new context or it simply pass the previous context. So that introduce another variable called CT, which is same as AT, which have the context vector information in the RNN. So CT is nothing but AT. So what happens? Uh, the new context information that you are calculating, uh, which how you calculate AT? You calculate AT by multiplying WA with AT minus 1 comma XT, which is nothing but the vertical concatenation of this multiply with the weight matrix, adding bias, passing to activation function gives you AT. So CT is also similar. So new information, a new context vector, we are calling it candidate context information. That this is candidate which should be updated or not, or whether this should be memorized or not. It is same as our the new weight matrix WC involved plus adding bias, passing to activation function gives you candidate context vector. Now, whether this new context vector should be used or the previous context vector should be used. For that, you have a gate, and gate is known as an update gate, and gate is having output 0 and 1, so that's why we are using sigmoid activation function. And since it is a learnable parameter, so it is learned during the training time, so that obviously there is weight involved, which is WU, uh, that takes ct minus 1 comma xt plus bu, and the output of this basically suggests that whether the information to be updated or not. And the ct calculated based on by multiplying update gate with the candidate value, that is the new information, or 1 minus u 1 minus tau u with the previous information. Though it equation looks non-trivial and complex, if you see here, it is quite easy to see. If you have update gate value 0, so what happens? So this term becomes 0, and this is nothing but ct minus 1. So your ct, which is a context vector from current RNA unit, is nothing but the previous uh, context vector from the previous RNA unit. So you are not updating with the new information. And if it is 1, then you are not taking the previous information, you are basically just only taking the new context information. Are you getting my point? So have you understood this? Yes or no? So that update gate is controlling whether information to be updated or not. So this update gate is either 0 or 1 most of the time. So we update the memory cell based on the update cell and the previous cell. So for example, let's say a sentence is there: the boy who played football in the rain slipped. So the slipped is basically relevant to boy, not with who and played. So when the word the processed, update gate value is 0 and the cell memory value is C. And when the boy comes as an input, update gate value is 1, and it is cell memory is updated with the new value or new information. And from after that, this information is carried out uh, till the word slipped, which have again the newer value, and updated value is 1 and updated by the newer value. So if you see here for slip, the context from boy is captured. However, you might ask how it is identifying whether boy is relevant to slip or why not 1 is here and not. So this is because of that we involved trainable parameter W wet matrix. During the training time, it learns the combination of the relevant words, and each time context vector is having small information compared to the RNA, which in turns indirectly solve the vanishing gradient problem. So this GRU is also known as a simple GRU, uh, where you are finding out whether which uh, word is relevant, which context information is relevant to this current word or current output. However, we are not. So this is a drawing for this simple GRU. Your CT minus one is equal to AT minus one, which is same. CT minus one and XT you have passed to 10H gives you the candidate context and contextual information. When you pass to sigmoid, gives you update gate. And that third equation that you have written here, we've written here, update gate multiply with the candidate information, and 1 minus update gate multiply with the old context information is represented by this, and this gives you CT. It could be CT minus 1 or it could be a new C till T. This, think of it as a gate which enables the pass of either C till T or CT minus 1. And this type of drawing is quite popular, which is easier to understand the GRU. So that simple GRU give the notion of how whether uh, CT is related to so should be updated or not. So you pick only one value. So in turns indirectly it calculates. So in turns it calculates whether particular word is relevant to another input or not. So output is independent on particular word or not. Basically the notion of relevance. But still it does not capture how much it is relevant. So right now it is capturing only whether it is relevant or not. So if it is relevant, the information is updated. If it is not, then it is not updated. So what we have described so far is simplified GRU. Full GRU contained a new gate which is used to calculate the candidate C. This gate is basically tells how relevant is CT minus 1 to CT. Right now we have just seen कि, okay, CT minus 1 is relevant to CT only. Yes or no. But how much the value in what proportion it is uh, relevant. That introduces a new gate called relevant gate, which in C till T we with the CT minus 1 we multiply with the relevant gate, and the relevant gate is also calculated using the same weighted sum plus adding bias, passing to activation function again sigmoid, which gives you value in between 0 to 1. That relevancy notion captures how much information, how much CT minus 1 is related to CT, and the updation remains the same. CT is update gate into candidate context information plus 1 minus update gate into uh, previous information. Now, together with GRU, in parallel, other researchers have come up with other architectures of to capture the long range dependency or to avoid the vanishing gradient problem. Uh, Here, if you see here, this uh, to update CT, it depends on the only one single value update gate, and the inverse of this is taken here. There is 1 minus u and u. However, there might be possibility that word might be relevant, or the output or context information might be relevant to the current information, current input, as well as the previous input both. Right now, in this case, update gate mostly which is 0 and 1. So either it will be replaced by the new context information, which suggesting that CT is not relevant to CT minus 1, or it will be completely replaced with CT minus 1, which has older information. So which suggests that CT minus 1 and CT are relevant to each other. However, if there is in between these two, so CT is relevant, somewhat relevant to the previous context information as well as the new context information both. So indirectly, it is saying it is relevant to the new current word or current token and then the previous tokens as well. So LSTM is another architecture where uh, have the notion of different gates, which makes it independent to calculate those two values. Uh, you might have seen GRU have introduced relevant gate or update gate. Researchers have tried with various number of options for gates, and they found out that this particular standard GRUs and full GRUs are the best one performing. However, as a researcher, what you can do, you can introduce new gates or experiment with a different GRU architecture or full GRU architecture based on the problem that you are solving. So you can, as a enthusiastic, uh, uh, taking an enthusiastic approach, you can come up with variants of GRUs, full GRUs. LSTM, which is long short term memory, takes another way to avoid vanishing gradient, which introduces some gates like update, forget, and output gate. And here the CT is not same as AT, and those two are two different things. And this is more powerful in general than the GRU because GRU uh, here the candidate information, the current context representation uh, is not only dependent on update gate, it checks for the forget gate as well. So update gate again a learnable parameter which takes AT minus 1 and XT passing to activation function gives you update gate, and the candidate context representation is nothing but passing to 10h WC multiplying with the AT minus 1 comma XT and gives you C till T. Similarly, forget gate and the output gate, all they have the same equations, and the notion of it is these are the learnable parameters which during the training time are learned whether what is the value of update gate and the forget gate and the output gate, and based on these values, new context information is basically uh, update gate multiply with the current context or newer value plus forget gate into previous context information. So now that unlike GRU where here you have 1 minus tau u, you have forget gate, a separate gate for it, which makes an independence between these two uh, computation. And when you pass this CT to take the 10h of this CT and then you multiply with the output gate, you get the context vector that is passed to the next RLE. And this is a diagram for it. So CT minus 1 and AT, these are two things that pass to the each RLE unit, where AT minus 1 and XT are taken and calculate for forget gate, update gate, and output gate, and forget gate and update gates further update gate whether it is going to be updated or not. This operations this it takes it till t and ct minus 1, right, and the update gate and the forget gate towards the end it calculates whether this ct is from here or here or the both. It takes the values, it could be a combination from both, and this ct is passed. And using the output gate, you calculate the output, which in turn goes to the softmax, calculate the YT. So in GRU, we have an update gate and a relevant gate and a candidate cell variable called CT. While in LSTM, we have an update gate U. Sometime it is also called input gate as well, and a forget gate and the output gate. So in some literature, you will find out the terminology called IFO instead of tau u, tau f, or tau o. So this is about LSTM, uh, and GRU and LSTM. Further, there are some variants called bidirectional LSTM and bidirectional GRU. So right now, what we have seen that okay, so we pass the context information in the one direction only. So these are the this is useful when your output was only dependent on the previous contextual information. However, it might be possible that the current output not only depends on the previous context but from the future context as well. So in that case, you can use bidirectional GIU, which where YT is not only takes AT from the previous context, but also the AT from the future context. That's where comes the bidirectional architectures, where this bidirectional RNN, or it could be a variant of RNN like LSTM or GRU, where YT is not only calculated based on AT from left to right, it is also calculated from AT which is coming from the right to left. And the same thing, same for other RNN unit as well. The others variants like right now, the each RNN unit might have single hidden layer input, hidden or output layer. If you have more number of hidden layers inside the RNN in each RNN unit, then it is known as a deep recurrent neural network. So today we'll end it here, and I'll share the slide. You can read about it, and after some break. You will see an implementation hands-on on LSTM, uh, basically the recurrent neural network for text classification task. So we'll take a break, uh, and meanwhile, if you have so before taking a break, if you have any questions, just write your questions on the chat. From my side, uh, introduction of LSTM, GRU, LSTM, and RNN is over. If you have any questions, you please ask. Uh, One is which one to use in which specific case. So LSTM is so it actually it depends on the problem context. So if you have a a problem such a way that where dependency of or relevancy is based on multiple words or the is a composition of multiple information from different tokens, then LSTM might perform better than the GRE. But again, machine learning or deep learning follows no freelance theorem, which says that there is no particular model for which performs best in general. uh, वो in general वाली जो बात थी वो LSTM की वो it is due to the calculation of CT which is not dependent on only update rate, though it is quite specific to problem that you are working, so you have to check it experimentally which one is working. कोई एक पर्टिकुलर एल्गोरिथम नहीं है कि जो या आर्किटेक्चर नहीं है जो सब पे अच्छा काम करेगा. Usually in small data with fewer classes or fewer output values, your LSTM might work better than the GL. But again, it is not the same case with each problem. Do the experiments and then you will find out. All right. So with hands on, it will be more clear. Yes. Also, we'll continue our session with the so this theory session in the next session tomorrow, theory, where we'll see how this RNN and variants of RNN can be used as a language model, and what are the problems that are these networks cannot solve, and why we have moved toward the transformer uh, like architectures. And we'll see the theory of those architectures as well. And from transformer, we'll discuss later on. We'll discuss about the LLMs and variants of LLMs. So this is how we'll move from language modeling to large language modeling. Okay. So no more questions. So we'll stop it here. Take a 5 minute break, and then we'll Mayank will continue with. Okay, so let's take a 10 minute break. So we'll start with uh, 4 p.m. and Mayank will take you to the hands-on demonstration. Okay, thank you. Yes, 4 p.m.